Lesson 2.3 covers some more connectives and how they apply to the truth tables. We're now going to look at a few more connectives. As before, in each definition, the variables P and Q always represent propositions. First, let's look at the implication. This is also called the conditional connective, and it's associated with the words if-then. An implication is the compound proposition if P then Q. And in symbols, we write this as a double-lined arrow. And some books vary. Some books use a single-line arrow for this. We define if P then Q to be false when P is true and Q is false. And it's true in every other case. I can also read this symbol as implies. So I could say P implies Q, or I could say if P then Q. It's only false when the proposition in front of the implication symbol is true and the proposition after the symbol is false. So when you have a true implies false, that's when the implication is false. So let's look at an example to better understand this. If you make a 90 or above, I will give you an A. Think of that as a contract that I'm making with you as your teacher. And let's consider every possible case. Well, first, the P and the Q could both be true. P is the first statement, if you make a 90 or above. Q is the second statement, I will give you an A. So the meaning in words, if P is true, you did make a 90 or above. Since Q is true, I did give you an A. So that contract held valid. It was not broken, so the implication is true. If both parts are true, the implication is true. Next, if P is true and Q is false. So that means the first part is true and the second part is false. So for this example, you made a 90, but I did not give you an A. Well, this time I broke the contract. So that statement that I made, the promise of if you make a 90 or above and I will give you an A, I broke that promise, so that was a false promise. So my implication was false. Well, now let's look at the two cases where P is false. Okay. This time, you did not score a 90 or above, but I still gave you an A. So P was false and Q was true. Well, I didn't break my promise. I simply, in the promise, didn't state what would happen if you didn't make a 90 or above. So the contract was made upon the condition that you must score a 90 or above. So the contract wasn't broken. If you didn't score a 90 or above, I was free to give you any grade I choose. I didn't make a condition based on that. So this implication is true. And then finally, if P and Q are both false, that means the first part and the second part are false. You did not score a 90 or above, and I did not give you an A. Well, like the previous case, since the contract was made upon the condition that you must score a 90 or above, the contract was not broken. I didn't break my promise because you didn't hold up the 90 or above. So I was free to give you any grade I chose. So the implication, that promise I made, was still true. There's other forms or other ways to phrase the implication. The most common wording for the implication is if P then Q. However, there are a few other ways it can be written. I could have P implies Q. That's the second most common. I could have P only if Q. I could have P is sufficient for Q. Q is necessary for P, and then I could have Q if P. In symbols, these would all be the P followed by the arrow and then the Q. Well, now before we look at the last connective, let's look at a few new definitions which use the implication. Consider again the implication: if I score a 90 or above, then the teacher will give me an A. The first part, if I score a 90 or above, is called the hypothesis. The second part, the teacher will give me an A, is called the conclusion. So the if part is the hypothesis, the then part is the conclusion. Well, what if we interchange the roles of P or Q? We're basically switching the hypothesis and the conclusion. When we reverse the roles of P and Q, we have the converse of the original implication. And so we may ask the question, does Q imply P have the same truth values of P implies Q? If I've got the statement or the promise of P implies Q, can I also assume that Q implies P? Is the reverse the same? So let's look at a truth table. Begin with P and Q, and P is true, true, false, false. Q is true, false, true, false. Now for the original implication, the P implies Q. Well, the P implies Q is only false when the first part is true and the second part is false. So find the row where P is true and Q is false, and that's row 2. This is when the implication is false. Our implication will be true in every other case. Well, now for Q implies P, that's only false when the first part, Q, is true and P is false. So this time I start with Q and compare it to P. So when Q is true and P is false, that's in my third row. So I have a true implies false, so that is false. It's going to be true everywhere else. So now back to my question, does Q implies P and have the same truth values as P implies Q? And that's no. If I compare those two columns, in the first row they are both true, and in the last row they're both true. But in the middle two rows they have opposite truth values. So in conclusion, an implication and its converse do not always have the same truth values. So if I know the implication is true, I can't conclude that the converse is true. And likewise, if I know the implication is false, I cannot assume the converse is false. Knowing the truth value of an implication doesn't tell me what the truth value of its converse is. So if I go back to that promise of if you make a 90, I will give you an A, I can't assume the opposite. I can't assume that if you make an A, you scored a 90 or above, because the converse was not always the same as the implication. Well, what if we negate the P and the Q? When we negate P and Q, we have the inverse of the original implication. And so I want to know, does the inverse, not P implies not Q, have the same truth values as P implies Q? So I begin my truth table with P and Q and their basic truth values. P is true, true, false, false. Q is true, false, true, false. Next, I need my original implication, P implies Q. Now, to build the contrapositive, I need a not Q and a not P. It doesn't matter which order you list these in. I list my Q first just because it comes first, and then a not P. That's going to make it easier when I do my final contrapositive of not Q implies not P. So for my original implication, it starts with a P and ends with a Q. So start with your P column and go to your Q column. You're looking for a true implies false, which is in row 2. That's the only time the implication is false. So it's true everywhere else. Next, my not Q is the opposite of Q. Since Q is true, false, not Q is false, true. Next, my not P is the opposite of P. Since P was true, false, not P is false, true. Now I'm ready for my final column, the contrapositive. Not Q implies not P. So begin with the not Q and compare it to the not P. You're looking for the true implies false. This time it's in row 2. So there's my false. And it's true everywhere else. So the contrapositive is true, false, true. So now back to our question, does the contrapositive have the same truth values of the original implication? When I compare these two columns, I see they are the same every single case. So yes. So our conclusion and implication and its contrapositive will always have the same truth values. We'll use this in a later section when we're dealing with logic proofs. If I know the implication is true, I can assume the contrapositive is also true. If I know the implication is false, I can assume the contrapositive is also false. Let's look at some examples of the implication, and specifically with its converse, inverse, and contrapositive. So for example, if we have the implication, if an animal is a fish, then it swims. Remember, the part that comes after the if is usually our P, and the part that comes after the then is our Q. So our P is an animal is a fish, and our Q is it swims. So let's look at part A. Part A states if an animal is not a fish, then it does not swim. I see the nots, and my original implication did not have nots, so I know I'm dealing with negations. So if you look at the first part, it says if an animal is not a fish. That's the negation of P, so that's not P. The second part says it does not swim. Well, it swims was our Q, so it does not swim would be not Q. So this statement is not P implies not Q. So I've negated each part of the original implication, so this is the inverse. In part B, if an animal does not swim, then it is not a fish. Well, I see the nots again, so I know I'm using negations. The first part, the hypothesis, is the animal does not swim. This is the negation of Q, so this is not Q. The second part, or our conclusion, is it is not a fish. This is the negation of P, so that's not P. So I have not Q implies not P. I've switched the order of my original implication, and I've negated both parts. That's the contrapositive. When you do both, when you switch the order and negate each part, you have the contrapositive. Then finally, if the animal swims, then it is a fish. Well, an animal swimming was my Q, and the animal being a fish was my P. So this time I have Q implies P, or if Q, then P. This is the reverse of my implication. I've switched the order. When I just switch the order, that's the converse. Let's look at the next example. If we win the game, then we will go to the tournament. So determine if the following statements are the converse, the inverse, and the contrapositive. So in the first part, if we win the game, we're going to let that be P. We will go to the tournament will be Q. So part A states, if we go to the tournament, then we won the game. Well, going to the tournament was our Q, and winning the game was our P. So part A gives Q implies P, or if Q, then P. So my original implication has been reversed, so this is the converse. In part B, if we do not go to the tournament, then we did not win the game. I see the nots, and my original implication did not have nots, so these are negations. The first part, not going to the tournament, is the negation of Q, so that's not Q. Then not winning the game is the negation of P, so that's not P. So this time I have not Q implies not P. So I've taken my original implication and I've switched the order and taken the negation of each side. So this is the contrapositive. In part C, if we do not win the game, then we will not go to the tournament. So not winning the game is the negation of P, so that's not P. Not going to the tournament is the negation of Q, so that's not Q. So this time I have not P implies not Q. I've taken the negation of each side but kept the order the same, so that's the inverse. In the final example, if it rains, I will not mow the yard. So I'm going to let P be if it rains. Generally, we always want our original P and Q to be positive. We don't want those to contain the word not. When we're doing the proofs in a future lesson, it's going to be easier to understand and less tricky if we let the P and Q always be positive. So I'm going to let Q be I will mow the yard. So in my original implication, if I have I will not mow the yard, that's not Q. So let's look at part A. If I mow the yard, then it did not rain. Well, mowing the yard was my Q. It did not rain. Well, if P is it will rain, then it will not rain is my not P. My original implication was P implies not Q. In this example, I have Q implies not P, so I've switched the order and negated them. That's the contrapositive. In part B, if it does not rain, I will mow the yard. Well, P is it will rain, so not raining would be not P. I will mow the yard was my Q. So this time I have not P implies Q. So I've kept the order the same but negated each side. That's my inverse. Then finally in part C, if I do not mow the yard, then it rained. Not mowing the yard was my not Q. Raining was my P. So this time I have not Q implies P. I've just switched the order of each side, so this is my converse. Next, we're going to look at the biconditional, and it's associated with the words if and only if. A biconditional is a compound proposition P if and only if Q. The symbol for the biconditional is a double arrow. There's an arrow at each end of it. This is one that many students make much harder than it actually is, and the confusion comes with the definition. Most textbook definitions are going to make the following statement. If both implications are true statements, then the biconditional is true. This definition is fine if you understand the terms in the definition. It says both implications are true. A lot of students make the mistake of thinking that the P and the Q both have to be true. But P and Q are propositions, not implications. So if I look at that definition again, the biconditional is true when each implication is true, not the propositions on each side of the biconditional, but the implications. So let's look at that word implication. That was the last connective we just covered. If I have the biconditional P if and only if Q, that's made up of two implications. Notice that's a double arrow, so it goes both ways. That means P implies Q, and read it the opposite way, Q implies P. So in order to use the book's definition, you have to do the truth table for P implies Q and Q implies P. And you've got to determine when they're both true at the same time. So let's do that truth table. So begin with P and Q. There's two propositions, so we have the 4-line truth table. I'm going to have to find P implies Q and Q implies P. Then I can find my biconditional P if and only if Q. So for P implies Q, it's only false when the first part P is true and the second part Q is false. So it's false in the second line of the truth table, and it's going to be true everywhere else. For Q implies P, you read this one backwards. Find the instance when Q is true and P is false. That's in the third line. So Q implies P is false in the third line and true everywhere else. Those are the two implications. P implies Q and Q implies P are the implications that the definition refers to. So you look for when they're both true. Those implications are only true in the first line and the last line. So that means my biconditional, my P if and only if Q, is only true in the first line and the last line of this truth table. So it's false in the second and third lines. Now this is a lot of work, and I don't really want to have to do the two implications every time I have a biconditional. So let's look at how that biconditional compares to my original P and Q. So I've taken out the two implications. So if you remember, P implies Q was true, false, false, true. Notice that the P if and only if Q was true twice and false twice. So we want to look at when that was. The biconditional was true when P and Q had the same truth values. So in line 1, P and Q were both true, and my biconditional was true. In line 4, P and Q were both false, and my biconditional was true. Well, the biconditional was false when P and Q were different. In line 2, P was true, Q was false. They had opposite truth values, so my biconditional was false. In line 3, P was false, Q was true. They had opposite truth values, so my biconditional was false. That's the trick I want you to learn. Rather than relying on the formal definition and having to find each implication, let's just compare the P and the Q. So you want to know when the biconditional P if and only if Q was true and when it was false based on the values of P and Q. And as we said, if P and Q have the same truth value, then the biconditional is true. If P and Q have opposite truth values, the biconditional is false. Before we move on to the truth tables for this section, let's look at a few more definitions. If a compound logic statement is always true, then it's considered a tautology. A tautology is a logic statement that's always true. No matter what the values for P and Q are, that final column of my truth table is always going to be true. If a compound logic statement is always false, then it's considered a contradiction. So if my final column of the truth table is all false values, no matter what P and Q are, then that original compound logic statement is a contradiction. If two logic statements have the same truth values, then they're logically equivalent. And as I mentioned, to determine each of these, we always look at the final column of the completed truth table. So let's look at our examples. I have P implies P and not Q. So begin with what's inside the parenthesis. I have P and not Q. So I know I'm going to need a not Q in my table. Then I'm going to need a P and not Q. And then I can do a column for my overall statement, P implies P and not Q. I have two propositions, the P and Q, so I have the 4-line truth table. The values for P were true, true, false, false, and the values for Q were true, false, true, false. So let's begin with not Q. Not Q is the opposite of Q. So if Q is true, false, not Q is false, true. Next, I want P and not Q. So I compare my P column to my not Q column. And is only true when they're both true. And this happens in my second row. The P and the not Q are both true in the second row. So the and is false everywhere else. Next, I want to look at P implies P and not Q. The P comes before the implication symbol, so I start with it, and I compare it to the P and not Q column. The implication is only false when the first value is true and the second value is false. This happens in line 1. In line 1, my P is true and the P and not Q is false. So the implication is false in line 1 and true everywhere else. So my final answer for this compound proposition is false, true, true, true. In the next example, I have a biconditional. In front of the biconditional, I have P or Q or R. Following the biconditional, I have P or Q or R. So take this one part at a time. Let's break down what's in front of the biconditional. In front of the biconditional, I have P or Q or R. Since the Q or R is in parentheses, I need to find it first. Then after I find it, I can compare it with the P. So my next column is going to be P or Q or R. Following the biconditional statement, I have P or Q or R. Since the P or Q is in a parenthesis, it needs its own column in the truth table. And then once I find the P or Q, I can compare that with the R. So I need a column for P or Q or R. Then my final column for the truth table will be that original statement, the biconditional. I don't have room on my screen to rewrite that entire statement, so I'm just going to put the biconditional symbol in that last block. Now to fill in my values, the value for P are true, 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 and then false, 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 false. Q alternates true and false values 2 at a time. So I have true, true, false, false, true, true, false, false. OR just alternates true and false. So true, false, true, false, true, false, true, false. Now I want to find Q or R. So I compare the columns for Q and R. The OR is true when either Q or R is true, and it's false when they're both false. This time, just to make it a little easier, let's look at when they're both false. They're both false in rows 4 and 8. That's when the Q and the R are both false at the same time. So that means my OR is going to be true everywhere else. Now for P or Q or R, I compare the P column with the Q or R column that I just filled in. And again, these are connected with an OR. So OR is only false when they're both false. Well, these are only both false in row 8. So for this column, it's true everywhere except the very last row. Next, I want to compare P or Q. So look at when they're both false, because this is an OR. They're both false in the last 2 rows. So that means P or Q is true everywhere else. Then next, I want P or Q or R. So I compare the column that I just got, the P or Q, to my R column. These are connected with an OR, so find when they're both false. They're both false in the last column. So that means this statement is true everywhere else. Finally, for my overall compound proposition, I look at my biconditional. To complete the column for the biconditional, I want to compare what comes before it to what comes after it. What comes before it is my P or Q or R, and what follows the biconditional is the P or Q or R. I compare these 2 columns and I'm looking for the places where these have the same truth values. Well, if you look at these columns, they always have the same truth values. Since they always have the same truth values, my biconditional is always true. When you're looking at a completed truth table, always look at the final column. If that final column is always true, you have a tautology. Now looking back at your truth table, you'll see that the columns for P or Q or R and the column for P or Q or R have the same truth values. So that means these 2 individual statements were logically equivalent. Let's look at another example. I want to create a truth table for not P or Q, if and only if not P or not Q. So I only have a P and a Q, so I'm going to have a 4-line table. Let's look at what comes before the biconditional statement. I have a not P or Q. So I need to start out by finding P or Q. Once I have that column, I can find its negation. I can find not P or Q. Following the biconditional symbol, I have a not P and then I have a not Q. So the not is with each individual variable. So I need a column for not P and a column for not Q. Once I have these, I can find not P or not Q. Then when I have these columns, I can find my final biconditional. And again, on my computer screen, I didn't have room to rewrite that entire statement. In your truth tables, in your notes, you should have room to print it. So go ahead and recopy the entire biconditional statement. So let's begin with P or Q. So I compare my columns for P and Q. The OR is only false when these are both false. That's in my fourth row. So it's true in the first 3 rows. Now I want the negation of P or Q. So look at your P or Q column and take the opposite truth values. So if I have true, 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 false, the negation of this is false, 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 true. In the next 2 columns, I'm going to negate P and then negate Q. So the opposite of P is false, false, true, true. And the opposite of Q is false, true, false, true. Now that I have these 2 negations, I compare them with the OR. The OR is only false when both sides are false. So look at when not P and not Q are both false, and that's in the first row. So it's true everywhere else. Now I finally move on to my biconditional. The biconditional is comparing the not P or Q with the not P or not Q. So look at these 2 columns. The biconditional is true when these 2 columns have the same truth values. So if you look in row 1, they're both false, so my biconditional is going to be true. In the last row, they're both true, so my biconditional will be true for the final row. In rows 2 and 3, these 2 columns have opposite truth values, so my biconditional is false. So for the biconditional, compare the columns for what comes in front of it and what comes after it. In our next example, I have not P or Q, if and only if, not P and not Q. I have 2 propositions, P and Q, so set up the 4-line truth table. And let's build our table by beginning with what comes in front of that implication symbol. I need a P or Q, and then I need the negation of the P or Q. After the biconditional, I have a not P and not Q. So I need a column for not P, and then I need a column for not Q. And then I'm going to compare these with an and. And then finally, I can determine my biconditional, my if and only if. So begin with the P or Q. We're comparing P and Q. The OR is only false when both of those are false, which is line 4. So P or Q is true, 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 false. The negation of this would be false, 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 true. So not P or Q is false, 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 true. Next I find not P. The negation of P is false, false, true, true. And then I find not Q. The negation of Q is false, true, false, true. In this example, I'm comparing the not P and the not Q with an and. And is only true in one case, and that's when they're both true. So look at the not P and the not Q. Those are both true in line 4. So that's the only time my and is true is in that 4th row or that 4th line. So it's false everywhere else. So not P and not Q is false, 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 true. Now for my biconditional, compare the column in front of it with the column behind it. So I'm comparing not P or Q to not P and not Q. The biconditional is true when these columns have the same truth values. Well, these columns always have the same truth values. That means these were logically equivalent statements, so the biconditional was always true. Since my biconditional was always true, my original statement, not P or Q, if and only if, not P and not Q, is a tautology. When the final column of your truth table is all true, your original proposition was a tautology. Let's look at our next example, not P if and only if P. This time I just have one proposition, so I need a two-line truth table. It needs to contain a P, a not P, and then my biconditional, my not P if and only if P. Well, for the two-line truth table, my P is true and false. So my not P would be the negation of P, would be the opposite of P, which is false true. Now I compare these two columns for my biconditional. The biconditional is only true when both columns have the same truth value. Well, for this table, there's not a case when both columns have the same truth value. They always have opposite truth values. So when I compare that P and the not P, I get a false for my biconditional each time. Since the final column was always false, not P if and only if P is a contradiction. When your final column is always true, you have a tautology. When your final column is always false, you have a contradiction. Now in our final example, we have P and Q if and only if not R. So to build this truth table, I begin with the three variables, the P, Q, and the R. I need a column for P and Q. I need a column for not R. And then I need a column for my original statement, the P and Q, if and only if not R. Well, fill in your values for P, Q, and R. P is true, 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 false, 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 false. Q is true, true, false, false, true, true, false, false. And R alternates true, false, true, false, true, false, true, false. So I begin with the AND. I'm comparing P and Q. The AND is only true when these are both true. That only happens in rows 1 and 2. The AND is true in rows 1 and 2 and false everywhere else. Next, my not R, look at your R column and take the opposite of these values. So not R is false, true, false, true, false, true, false, true. Finally, for my biconditional, I'm comparing these two columns I just completed. I'm comparing the column for P and Q with the column for not R. The biconditional is true when these are the same. These two columns have the same values in rows 2, 3, 5, and 7. In row 2, they're both true. In row 3, they're both false. In row 5, they're both false. And in row 7, they're both false. So when they're the same, the biconditional is true. So that means it's false everywhere else.